Good morning, Ken Lasseson here. I am going to be going through a recent addition to the site and actually some interesting, clever research. We know bacteria impacts each other, and one of the ongoing problems has, although we know they impact each other, how much they impact each other, we tend to have difficulties finding, and you'll see shortly why. It's not so much that the information is hiding. The information is just not in a straight linear relationship. It is a more complicated relationship, just like in terms of determining ranges. It's not a matter of finding the average and calculating two standard deviations, which is the classic way of doing it for most things in life and nature and science. But it actually, in my case, I ended up using the the Kelthoff-Moultrie algorithm in order to determine what the range of normal or abnormal is. Similarly, I'm going away off the usual paths tread in this post to show what I found, which produces, as with the Kelthoff-Moultrie bounds, interesting and probably superior results than most of the literature and other methods are using. Okay, let's first start. We have a whole bunch of samples of different people and the same bacteria, and they shared certain bacteria. And what we do is, for each sample, we go and grab one particular bacteria, call it bacteria X, another bacteria called Y, and we go and take all just X, Y, these two bacteria values, extract them as a data. So we just have a row of data, nothing fancy, and we go and we plot them. So we're saying, okay, what's the relationship between two? The values both come from the same sample. So we are very specific and seeing how the two of them appear to influence. So now if we go down and there will be a link in the notes on where this page is, you'll see that when I plotted it using Excel, that we have practically no relationship at all, and r squared, the correlation coefficient, is practically zero. In other words, the immediate result will be somebody will conclude, nope, no relationship. And people won't necessarily go and plot all of them. You can see almost it looks like we have a relationship here, but if you look at the classic computations, no. Somebody could go in and manually remove outliers one by one, but in this case, looking at the sample base I have, you have approximately 2,600,000 different charts you have to examine and hand trim. So nobody's going to do that. They're going to just trust the algorithm, trust the numbers, and that's it. And after looking at the numbers, we find no relationships. Not quite. Okay, now the alternative approach comes from the concept actually came from my master's degree ages ago, and it looks at trying to match the curves, match the numbers, the relationship, by applying a monotonic increasing function to each of the functions, and then seeing if we get a correlation. This type of approach is often done with logistic regression, except logistic regression doesn't produce good results either. However, being creative in looking at alternative monotonic increasing functions, we will suddenly get the same data transformed into a high degree of effect, or correlation of 0.41. In plain English, it means that we can account for 41% of the bacteria change, or bacteria volume count, of one bacteria by looking at the amount of alternative bacteria. In other words, they're influencing each other. We don't know if A influences B or if B influences A, but we know that there's a relationship going on between them. And I tend to prefer to assume that they mutually interact with each other, which is what the model of the microbiome generally would imply. So basically, it's there. We finally find our relationships, which is in itself a bit of a interesting breakthrough, especially when we find that we have 226,000 relationships discovered using this approach. And these relationships, which account for at least 10%, are square root of 0.1 or higher. So now, here is an example of some of them. Some bacteria, we have a ton of relationships with other bacteria, and others do not have a ton of relationships with other bacteria. Some has none that can be determined, very independent ones. But we do find many do have relationships. And discovering relationships often depends on data size. I was restricted in having to have 100 points as a starting point for each comparison. Fortunately, I have a large enough data set that I've had a large number of candidates as a result. And what it gives, it allows us to calculate or to estimate how much a change of one bacteria will impact the other bacteria. Not a change in absolute units, but a change in transformed units for both factors. So the question is, where do you, now that I have all this data discovered, it's in my database, where in the world do you find this information? Well, let's hop over to the site. Let's look up a bacteria. Let's take our usual friend Lactobacillus. And there we have it. And what we have here is we have a new link which says how many interactions with every bacteria is there. So it's sitting right there. And you can go in, you can just click it. And now we see all of the interaction. And I've also calculated the impact, which basically comes from the slope times the percentage there. I simplified the mathematics down. What you will notice is this is the family which the genus Lactobacillus belong to. You see it's a very high percentage. And you may naively assume that women isn't Lactobacillus and these identical same? No, there's two other families of bacteria in there. And those families of bacteria is why we only have this one bacteria being 63%. There's three families. One accounts for 63%. The other two for the other 36%. So it is consistent with what we understand. And we have some good results. We have some negatives too. In other words, if a lactobacillus goes up, these bacteria goes down. So we are sweet and good. Now, let's go over and go back and look at a different bacteria. Here is another bacteria, and you can see again we have 238 impacts here. And if you go down towards the bottom, you will see a long list of 365 items which are impacted by it. So we really don't need any more information. What we are going to do is, if this list is short or empty, we see if we can use the associations to find things that will indirectly modify it. And by that I mean some item, let's say a particular antibiotic decreases a bacteria which is associated with the bacteria we are interested in, and there's a strong relationship. It implies that because we are reducing that one, our other one would also go down as a natural consequence, since there's a relationship between the two of them, both will go down or both will go up together if it's a positive, or the reverse if it's a negative. So we now have the aspect of being able to make forecasts of modifiers which will impact things which we have absolutely or very little literature on what impacts it. Probably most of the time because nobody has ever tested it, what I refer to as a orphan bacteria. Nobody has become interested enough to spend time on it, and there's a large number of bacteria, so that's not unexpected. Okay, now we're hopping over to one more bacteria, and this time when we go down, we see a new image showing up here. And the image is listing bacteria-associated modifiers. In other words, there's no explicit study on how this came along. And what we have is we have a few specific direct citations on it, things affected, and there's the number, it would probably be 5 or less. I think it actually works out to be 4. And if it had 5 or less, I then applied this bit of magic to increase it. So we now have other things being added to it, and these other things are things which in theory would probably result in an increase of this particular bacteria. And that's basically it. Now, if we want to know which bacteria are we picking, easy, sitting right there. 48, association 48. So here we have all the other bacteria which are associated, and if it's positive or negative. And what I do is I go to each one of these, look up everything that multiplies that, and then aggregate all of that together into a single value. And voila, we now have the expected impact. Okay, so now we have, you can see what interacts. You can now see what is implied of stuff that will interact. But wait, one more thing. What if you want to actually use this information for your suggestions? It's there as an option. It's not built in to automatically apply to you because it's a bit of speculation, and it's up to you if you want to make use of speculation. So here we could hop into Biome site demo account, which is always free to make use of. Go to that. We go down and we take one of these, and we'll go in and we'll go into advanced suggestions. And in advanced suggestions, what you will do is you will see under bacteria modifier scope, you see this brand new item sitting there. Include items associated by bacteria. It uses the same icon. You just go and click that, and away you go. So first, what I'm going to do is, and no need for both of those, is I'm going to click here and show the first suggestions of things coming in, and then I'm going to go and add in this one, and it may or may not make a difference. It depends on what bacteria shifts are there. And looking at the two of them side by side, just flipping back and forth, it actually appears to make absolutely no difference. Probably because there's none of these oddball bacteria in there. There's 660 bacteria which now have modifiers, or at least 5 modifiers or more, which you do not have it. So that's basically it. You may see changes here, you may not see changes here, but it just gives you another way of finding modifiers or changes of diet, supplements, when there's an absence of information. Worth comparing to see if anything changes. The impact will probably not be huge, but in some cases, it may be an essential change. Okay, at that point in time, I'm going to shut up and get back to my cup of coffee that's getting cold beside me.